this is the 10th module of the course on econometric modeling. This is the last module of the second part, which is overview of classical linear regression model. So, here we are going to discuss hypothesis testing. Hypothesis testing is basically we are not going to get into any testing procedure right away. As you can see that the testing procedures are probably discussed at length in part 4, where we are getting into statistical inferences in a big way. So, I am here right now just going to introduce you to the concept of hypothesis testing, that is what is hypothesis, how the testing is generally done without talking about any specific distribution or testing procedure. So, this is the 10th module on hypothesis testing. So, we begin with hypothesis testing on beta. It can be alpha and or beta. Most often we talk about beta only. Hypothesis is actually a statement that proposes a possible explanation for an observed phenomenon and should be statistically testable. In statistics, hypothesis is about a population parameter and never for sample statistic. So, whenever we form the hypothesis, they are with respect to the population parameter beta or alpha. We have two types of hypothesis when we go for testing of hypothesis. One is null hypothesis. A null hypothesis is a statistical hypothesis that is tested for possible rejection under the assumption that it is true. So, since null implies void, so most often the way null hypotheses are formed, that should ideally be rejected. It is always stated as equality. And we have the second type of hypothesis while testing for hypothesis, and that is alternative hypothesis. It contradicts the null hypothesis or represents the remaining outcomes of interest. So, null hypothesis is the void hypothesis which we generally expect to reject, while alternative hypothesis is probably the alternative that we are expecting to come out. Consider the following regression results, that is y t hat equals 20 plus 3 plus 0.5091 x t. So far this is basically the estimated part of the observations on y that we have discussed. Now, we did not talk about how good this estimated value of 0.5091 is. So, this is a time when we actually just introducing you that how we can test whether how good this estimated parameter is. The reliability of these estimates is measured by the coefficients standard errors. Suppose it is of interest to test the hypothesis that the true value of beta is in fact 0.5. The following notation would be used. This is how we write a null hypothesis H naught, which is beta equals 0.5. So, see that though we are trying to test whether we are working with the estimated parameter, that is 0.5091, which is actually denoted by beta hat, the null hypothesis is for the population parameter and not beta hat, its estimated counterpart. And H1 is the alternative hypothesis, and this is beta not equal to 0.5. This would be known as a two-sided test, since the outcomes of both beta less than 0.5 and beta greater than 0.5 are subsumed under the alternative hypothesis. So, not equal to 0.5 simply implies that it could be greater than 0.5 or less than 0.5, both the possibilities are kept, and that is why it is called a two-sided hypothesis or two-sided test. Alternatively, a one-sided test would be like H naught is beta equals 0.5. So, null hypothesis is always in terms of equality, while the alternative hypothesis is either beta greater than 0.5 or beta less than 0.5. Here the null hypothesis that the true value of beta is 0.5 is being tested against only one of the two alternatives. There are two ways of testing a hypothesis, that is two alternative approaches, they lead to the same results, test of significance approach and confidence interval approach. Both methods center on a statistical comparison of the estimated value of the coefficient and its value under the null hypothesis. So, it compares the estimated value of the coefficient with a statistical value that is given by the distribution or whatever testing procedure we follow. In order to test hypothesis, assumption 5 of the CLRM, that is classical linear regression model, must be used, that is UT follows a normal distribution with 0 mean and constant variance equal to sigma square. Now, this is actually not something we are going to readily use, but to begin with we can follow this assumption. Since YT depends partially on UT, it can be stated that if UT is normally distributed, YT will also be normally distributed. And if you remember, alpha hat and beta hat or alpha beta are population parameters. Alpha hat and beta hat are estimated, they can vary from sample to sample, but for from one sample or for one particular sample, xt is a variable, we can consider it to be non-random once the sample has been collected. So, UT follows normal distribution and that is how YT would follow normal distribution. Further, since the least square estimators are linear combinations of the random variables and linear combinations of the normal random variables are also normally distributed, we have alpha hat and beta hat also following normal distribution with mean and variance 0 and sigma square. Okay. This is actually sigma square beta hat and sigma square alpha hat, because we know that the variance of alpha hat and beta hat are not exactly sigma square, we can denote it them by sigma square alpha hat and sigma square beta hat, while the sigma square beta hat is actually equal to sigma square divided by summation x I minus x bar whole square, and similarly we will have an expression for sigma square alpha hat as well. Okay. So, we for the time being formally assumed that alpha hat and beta hat also follow normal distribution, and that is because we have a large number of, or we can have a large number of alpha hat and beta hat when we go for repeated samples from the same population. Now, standard normal variables can be constructed from alpha hat and beta hat by subtracting the mean and dividing by the square root of the variance, and then replacing the square root of the variances by their sample counterparts, that is the calculated standard errors of the estimates. So, what we obtain here is this, that is alpha hat minus alpha divided by standard error of alpha hat and beta hat minus beta divided by standard error of beta hat. Now, these two follow t distribution with t minus 2 degrees of freedom. Why they follow t distribution, that we would discuss at length while discussing t test in part 4, while we deal with statistical inference at length. As such, for the time being, we are also not going to use these assumptions or these expressions much. Just to begin with, I am introducing these concepts. So, this implies that alpha hat and beta hat follow a t distribution with t minus 2 degrees of freedom. Okay. So, under this approach, first the test statistic is calculated. Say for beta hat, the test statistic will be beta hat minus beta divided by standard error of beta hat. Now, you would say that we do not know the value of beta. So, for that we have the null hypothesis. So, the null hypothesis is always about beta. So, if the null hypothesis is beta is equals to 0, then my test statistic will be beta hat minus 0, that is only beta hat in the numerator, divided by standard error of beta hat. If the null hypothesis is beta equals to 0.5, then my test statistic is beta hat, the calculated or estimated value from the regression, minus 0.5 divided by the calculated standard error of beta hat, right. So, we can always construct a test statistic given the null hypothesis or under the null hypothesis. Then a significance level is chosen. Level of significance is defined as the probability of rejecting a correct null hypothesis. It is often denoted by alpha and not to be confused with the constant term alpha in a regression model. So, significance or level of significance is also denoted by alpha, and traditionally the level is chosen to be 5% or 0.05%, but one can go for other significance levels also. The other two most commonly used possibilities are 1% and 10%, right. Now, given a significance level, a rejection region and a non-rejection region can be determined. If a 5% significance level is employed, this means that 5% of the total distribution, that is 5% of the area under the distribution curve, will be in the rejection region. And if my test statistic falls in that region, we will be rejecting the null hypothesis, otherwise we will not. So, this is actually explained using diagram. So, first we explain the two-sided hypothesis. So, this is we are measuring x on the horizontal axis and the frequency on the vertical axis, the way a distribution curve is generally drawn. And it may follow normal distribution, it may follow t distribution. I am generally going for a nice bell shaped curve for the timing. So, if it is a two-sided test at 5% level of significance, then what we do is that we divide 5% for both sides. So, we have 2.5% at each side. So, 2.5% rejection region and this is another 2.5% rejection region, and in the middle we have 95% non-rejection region, and I calculate the test statistic on the basis of the null hypothesis or under the null hypothesis. If my test statistic falls in either of these regions, then I will reject the null hypothesis, otherwise I will not reject the null hypothesis. Okay. So, we call it the non-rejection region. Now, how do I understand whether it falls here? Of course, I will be having a critical value corresponding to these points, right, and then if my calculated test statistic is larger than either of these two critical values, that is smaller than this critical value and larger than this critical value, that means my test statistic is falling either in this region or in this region. Now, we go for one-sided 5% hypothesis testing, that is again the significance level is 5%, but this is a one-sided test where the alternative hypothesis is beta is less than beta star. So, we have here only 5% rejection region, that is on the left, and 95% rejection region consists of this entire region. Similarly, we again go for another one-sided 5% significance level hypothesis test where the alternative hypothesis is beta is greater than beta star. So, of course, we will be considering the right hand tail, and this is my 5% rejection region and the rest is actually 95% non-rejection region. So, graphically this is what we actually plan to do or try to do. So, the standard error is a measure of how confident one is in the confidence coefficient estimate obtained in the first stage. If a standard error is small, the value of the test statistic will be large relative to the case where the standard error is large. You remember, while we calculate the test statistic, we have beta hat minus beta divided by standard error of beta hat in the denominator. So, if standard error of beta hat is small, then this entire thing is large. Alternatively, if standard error of beta hat is large, then the entire things becomes small, right. So, that is what is being mentioned here, that for a small standard error, it would not require the estimated and hypothesized values to be far away from one another for the null hypothesis to be rejected. The significance level is also sometimes called the size of the test, and it determines the region where the null hypothesis under test will be rejected or not rejected. A significance level of 5% means that an extreme result would be expected only 5% of the time as a consequence of chance alone. For example, if the 5% critical value for a one sided test is 1.68%. So, I mentioned that in this bell shaped curve there will be critical values, right. So, suppose the critical value is 1.68 here. This implies that the test statistic would be expected to be greater than this value, that is 1.68, only 5% of the time by chance alone, right. One potential problem with the use of a fixed, for example 5% size of test, is that if the sample size is sufficiently large and null hypothesis can be rejected as the standard error reduce with the increase in sample size. Therefore, some suggest that a lower size of test, for example 1%, should be used for large samples. So, for large sample we would recommend going for a lower sample size for the reasons explained here. Now, coming to the interval estimation. So far we were talking about significance level approach, now we are getting into confidence interval approach. Interval estimate as opposed to a point estimate gives a range of values or interval for the sample estimate. The interval estimated is called confidence interval. Thus, confidence interval for a parameter is an interval computed from sample data containing the true value of the parameter with certain level of confidence. For example, if beta is equals to 0.93 with 95% confidence interval as 0.77 to 1.09, which implies that my beta hat, which is 0.93, actually has a confidence interval which runs from 0.77 and 1.09, right. Then it means in repeated samples 95% of the time the true value of beta will be contained within this interval. So, it is actually the long, it is between this interval, this is actually close to the true value. Constructing a 95% confidence interval is equivalent to using the 5% level in a test of significance. So, they are basically the same concept. 5% significance level tells us the possibility of rejecting a correct null hypothesis, while 95% confidence interval tells us that we can say with 95% confidence that our estimated or the true parameter will actually lie within this interval. So, confidence interval is actually equal to 1 minus significance level or 1 minus alpha. The endpoints of the confidence interval is the confidence limit. So, where we are actually drawing the lines for critical values, or this is basically the beginning of significance level and also the beginning of the confidence interval. So, confidence interval this way, significance levels this way, and these are called confidence limit. This is lower confidence level limit, this is upper confidence limit. Confidence interval is computed as sample estimate plus minus confidence level, that is say 95% multiplied by standard error of sample estimates. So, the lower confidence limit, that is this, is sample estimate minus confidence level multiplied by standard error of sample estimate, and the upper confidence limit is sample estimate plus confidence level multiplied by standard error of sample estimate. So, this is upper confidence limit. So, if I reduce my significance level to 1%, then my confidence interval would be 99%. So, as I reduce the significance level, my confidence interval actually grows. The test of significance and confidence interval approaches always give the same conclusion. Under the rest of significance approach, H naught or the null hypothesis is beta equals beta star will not be rejected if the following condition holds. So, we are trying to draw analogy between significance approach and confidence interval approach. So, we generally write that T critical, as I am trying to explain you that I have my T critical here. If it follows a T statistic, then I have T critical value here and T critical value here. Note that which are where I am drawing the T critical values, they are actually equivalent to lower confidence limit and upper confidence limit, right. So, what we say under significance level of significance approach is that if my calculated test statistic, which is beta hat minus beta star divided by standard error of beta hat, if it lies within this region, then I am not going to reject the null hypothesis. So, minus T critical greater than equal to the test statistic less than equal to plus T critical, right. So, for this the H naught, that is null hypothesis, beta equals beta star will not be rejected. Now, if I rearrange terms, then I have minus T critical multiplied by standard error of beta hat, it goes to this side, it goes to this side also. So, plus T critical multiplied by standard error of beta hat, I am left with beta hat minus beta star in the middle, or I take beta hat to this side. So, beta hat minus T critical multiplied by standard error of beta hat plus T critical multiplied by standard error of beta hat and beta star at the middle. This is the confidence interval approach. So, we can deduce the level of significance approach, or from the level of significance approach the outcome of the confidence interval approach. So, that is why we say that they both actually give the same results, right. So, this is basically a table which shows or which compares the test of significance and confidence interval approaches. So, this is where we this is how we first calculate the test statistic. Suppose beta hat is 0.5091 and standard error of beta hat is 0.2561, then the test statistic can be calculated as minus 1.92. Then the we find T critical as plus minus 2.086. So, we do not reject the null hypothesis since the test statistic lies within the non-rejection region. Now, for the confidence interval, we again continue with the same example. We find T critical, which are given here, and then we calculate the confidence interval as minus 0.0251 to 1.0433, and since my beta hat lies within this interval, so we do not reject the null hypothesis since the test statistic lies within the non-rejection region. It basically leads to the same outcome. Graphically, what we show is that this is 95% non-rejection region. This diagram I have almost drawn on every slide, and this is my confidence interval. So, this is confidence interval and this is the rejection region 2.5%, 2.5% here. I have also mentioned here the critical values, now which implies that these two add up to the significance level. So, again they give us the same results, confidence interval versus test of significance. Now, I talk about certain terminologies. A null hypothesis is either rejected or not rejected. It is incorrect to say that the null hypothesis is accepted. So, so far you have also seen that while drawing that bell shaped curve, I have always mentioned non-rejection region and never have mentioned acceptance region. So, null hypothesis is accepted is incorrect. When we not reject the null hypothesis, it actually does not mean that we accept the null hypothesis. This is also possible that some alternative null hypothesis can also not be rejected. So, between two alternative null hypotheses, which one we are going to accept? We basically do not reject it. For example, my null hypothesis 1 is 0.5, beta naught say 0.5, and one null hypothesis, and the other null hypothesis says that beta naught is 0.6. Now, if suppose I do not reject any one of them, or given the test statistic I fail to reject any one of them, but both of them cannot be accepted simultaneously. So, that is why we say that we have not rejected this, we have not rejected this. We actually do not become very affirmative about the fact that we have accepted them, because we are not sure about between these two which one can be accepted, and it is quite possible that both of them are not rejected. If a null hypothesis is rejected at 1%, it is obvious that it would be rejected for a larger size of the test. Similarly, if a null is not rejected at 5%, it will not be rejected at test sizes smaller than 5%, say 1%. If the null hypothesis is rejected at 5% level, it would be said that the result of the test is statistically significant. If the null hypothesis is not rejected, it would be said that the result of the test is not significant, or that is insignificant. So, these are the terminologies that we use. If we do not reject a null hypothesis, we say that the result of the test is insignificant or not significant, and vice versa. Now, we talk about type 1 and type 2 errors. Type 1 error is rejecting a true null hypothesis, probability is alpha. So, the type 1 error is the probability of rejecting a correct null hypothesis. Alpha, the significance level, measures the tolerance for or probability of committing a type 1 error. So, the moment we specify significance level at 5%, this means that the probability of rejecting a correct null hypothesis is only 5%, which is considered to be pretty low and generally created by or resulted because of certain randomness in the results obtained or data generated. Type 2 error is not rejecting a false null hypothesis, probability is beta, that is type 2 error measures the probability of not rejecting a null hypothesis which is actually incorrect or false. So, 1 minus beta measures the power of the test defined as the probability of rejecting an incorrect null hypothesis. 1 minus beta is the probability of rejecting an incorrect null hypothesis, beta is the probability of accepting a false null hypothesis. So, this is how we prepare a table. This is a situation where null hypothesis is true, we are accepting it, not making any mistake. We are rejecting a correct null hypothesis, we are making type 1 error. The null hypothesis is false. So, when we accept a false null hypothesis, we make type 2 error. If we reject a false null hypothesis, then there is nothing wrong in it. A significance level of 5% implies that it is only 5% likely that a null would be rejected when it was in fact true. What happens if the size of the test is reduced, say from 5% to 1%? The chances of making a type 1 error would be reduced, but so would the probability that the null hypothesis would be rejected at all, thus increasing the probability of type 2 error. So, there is always a trade off between type 1 and type 2 errors while choosing a significance level. The only way to reduce the chances of both is to increase the sample size or to select a sample with more variation. Now, we talk about the final thing, that is the p value or the exact level of significance. P value stands for probability value. It is the exact probability of committing a type 1 error, that is the probability of rejecting a correct null hypothesis. It is also defined as the lowest significance level at which the null hypothesis can be rejected. If the test statistic is large in absolute value, the p value will be small and vice versa. So, p values are most often reported by the softwares, whatever software you use, you would see that a p value is reported. So, on the basis of the p value reported, we can determine whether my null is rejected or not rejected at what significance level, 5%, 1%, 10% and so on. So, p values are basically the exact probability of committing a type 1 error. A very small p value implies the probability of committing a type 1 error is absolutely or almost 0, and this happens when the sample size is very large. So, that brings us to the end of module 10 on hypothesis testing. These are the books that I have followed for the discussion on these topics. Thank you.